So here's the video for assignment 10, and there's a bunch of different stuff in here. We talked about some of it, but some of it I'd like to take further. Um, and yeah, so it's a whole bunch of functiony stuff, a little bit of graphing. But I want to start with symmetry. We've got x-axis symmetry, y-axis symmetry, and origin symmetry. What do those look like? Well, x-axis symmetry is when you reflect across the x-axis, like this. So this point up here reflects over to be this point. 4, 2 becomes 4, negative 2. Okay, and we could summarize that by saying things that have x-axis symmetry, f of x equals negative f of x. Positive y value, negative y value at the same x value. That's x-axis symmetry, but notice this isn't a function. It fails the vertical line test, so not a function. Okay, y-axis symmetry. Well, with y-axis symmetry, we reflect across the y-axis. Now, when we do y-axis symmetry, please notice it's the x value that changes sign on y-axis symmetry. The x-axis changes sign, the x value changes sign for y-axis symmetry. So we say f of negative x gives you the same y value as f of x. Okay? And then finally, origin symmetry. When we think about origin symmetry, we're thinking about reflecting through the origin. So this point reflects through the origin to become this point. If this is 2, 8, then this is negative 2, negative 8. That's origin symmetry. And so what we're doing is we're changing the sign on both the x's and on the y's. Sometimes I see this written as negative f of negative x equals f of x. That's changing both signs. But sometimes I see it written as that. So if we change the sign on the x's, the y value will be opposite what it normally is how those people describe it. I tend to find this notation a little more understandable. I'm changing both signs with origin symmetry. Okay, now we've reviewed our symmetry types, and what about functions? Do you remember even and odd function? Well, it turns out that even and odd functions show up in AP Calculus and on the AP Calculus exam. So this is an even function. It's an even function because it has y-axis symmetry. That's what an even function is. An even function is not an even function because it has an even exponent. An even function is a function that has y-axis symmetry. Now, functions that have origin symmetry are odd functions. An odd function has origin symmetry. Okay? So we need to know even functions and odd functions. And we're not worried about x-axis symmetry because that's not a function. So we're not going to have anything that corresponds to function description for something like this. Now, I'm pretty sure that if I give you a part of a graph, like to 0, 1, 1, 0, 0, and I say, hey, look, here's f of x. Oh, did I forget to tell you? F of x is an even function. Will you finish the graph of f of x as though it were an even function? Sure, even functions, I know two things. One, they reflect across the y-axis, and because they reflect across the y-axis, I'm going to be changing the signs on the x values. I'm not changing the y's, just the x's. And so there we go. Y-axis symmetry. Oh, did I say x-axis symmetry? Oh, this is y-axis symmetry. So what would x-axis symmetry look like? Well, then I'm folding it down here, and I'm changing the signs on all the y values. So I still have 1, but now I have -1. So there's x-axis symmetry. And if we're looking at y-axis symmetry, we saw that one over here. And if I wanted to do origin symmetry of f of x, my origin symmetry would change both the x and the y signs. So I'd have -1, -1. So we can finish this graph 3 ways. It's not a function, but it has x-axis symmetry. It's an even function because it has y-axis symmetry. It's an odd function because it has origin symmetry. Notice with origin symmetry, we're changing both the x's and y's. Notice with y-axis symmetry, we're just changing the x's. And with x-axis symmetry, we're just changing the y's. Okay? So what if instead of giving you a graph, I give you a table of values? -2, -1, 0, 1, 2. These are y's and these are x's. 4, 1, -2. Okay, so what if I tell you that this graph is an even function? Can you finish filling out the table because this is an even function? Why don't you pause the video for a minute, give it a try, and come back when you're done. Okay, so if this is an even function, it has y-axis symmetry. And what I know about y-axis symmetry is I change the sign on the x and get the same value. I change the sign on the x, but have the same y value. So now I finished this graph as though it had y-axis symmetry. So this is an even function now. If I were to graph it, -2, 4, -1, 1, and 0, -2. So this is what I'm looking at. But when I reflect across the y-axis, I change the sign on the x's, and I get the same y value. I change the sign on the x's, and I get the same y value. I guess that's supposed to be more like that. Okay. What if, instead of completing this graph so that it was an even function, can you complete this graph so that it's an odd function? Will you please take a moment to finish this graph as though it's an odd function? Nice. So with an odd function, we change both the x's and the y's signs. Here, a -2 became a +2, and a -1 became a +1, but I have to change the signs on these as well. Now I have an odd function with origin symmetry. Okay? You should be prepared to deal with this. Sometimes AP likes to say, hey, here's f of x, and then they say, oh, by the way, f of x is even. And they put that up in the stem of the problem, and then they say, okay, we'd like to know about any maxes. Any maxes? And sure, you tell them this max over here at 2, 5. But because we know this is an even function, we know that there's another max over here at negative 2, 5. They don't tell you, they don't show you. Yes, they do tell you. They say the function is even. And it's up to you to know that an even function has y-axis symmetry. So you won't just have one max over here, but you'll have two maxes to contend with. Okay? We'll start seeing that in chapter 5, probably in November. All right, now I wanted to take a look at graphing some other things. I have a bunch of functions here. Most of them are functions, one of them's not. And I want to talk about graphing them. Now, of course, I'm sure you could pull out a calculator and graph this. My only concern with you pulling out the calculator, as we experienced with our first assignment, is that the calculator often doesn't give us the full story. So if I go to y equals, and I type in x square root 9 minus x squared, okay? Just thinking about this, I see a semicircle times a linear function. I'm not really sure what it means when I multiply a linear function times a circle. But what I can say is, if I do zoom standard here, I see this. See the gap there? See the gap there? Yeah, there's no gap there. It looks like there's a gap there. Here, I'll turn on the light. See the gap now? Yeah, that doesn't really exist. If I change my viewing window and go -3 to 3, -3 to 3, I guess I need more y. Let's change this to -4 to 4. And the y values, -8 to 8. See, it looks a lot like there's a gap in these places, but there is no gap. And how do I know that? Well, that's an x-intercept over there. How do I find an x-intercept? I find an x-intercept by setting y equal to 0. And then, how do I do this? Well, I set each factor equal to 0. This is easy enough. I see that x-intercept. But look here, if I square both sides, and then add x squared to both sides, and then take the square root, don't forget that plus or minus, I get plus and minus 3. So this is a connected graph. There's no gap. What do we know? We know there are x-intercepts at -3, at +3, and at 0. Now if I plug in a positive number between 0 and 3, like 2, I'm going to have a positive. 2 squared is 4, 9 minus 4 is 5, square root of 5, square root of 5 times 2, that's positive. So I'm going to have something up here. But if I plug in a -2, this will still be positive because of this squaring, but I'll have a negative times a positive, and I'll have -2. In fact, it turns out that this is an odd function. And I can tell that this is an odd function because this point reflects through the origin to this point, and this point reflects through the origin to this point. But I could also check this way. The test for origin symmetry is if I change both x and y signs. Okay, so I'm going to come up here and I'm going to change y sign, x sign. Okay, so let's see what happens. Negative x times negative x is positive x squared behind this minus sign. So now I've got this. And if I divide both sides by -1, these cancel. I get y equals x square root 9 minus x squared. See, that's the original. When I plugged in a negative x and negative y, I got back to the original. Therefore, this has origin symmetry. Okay? All right, so we've got origin symmetry. You can, of course, use your calculator to find these mins and maxes. That will be important for us through the year that you can do that. Second, calculate minimum. Move your cursor to the left side of that minimum. Hit enter. Move to the right side. Hit enter. Do you want to guess? No, of course not. And hit enter. And so I see the ordered pair here is negative 2.121, comma, negative 4.5. And then this point, because we have origin symmetry, this point must be 2.121, comma, positive 4.5. Okay? So there's my well-labeled graph. Half of the AP exam is with calculator, half is without, approximately. And so we need to be able to do things with our calculator as well as by hand. What about this one? How about y equals x to the fourth minus 4x squared? How can we graph that without our calculator? Well, the first thing I'd like to do is some GCF factoring. And then I notice this difference of squares. So where are my x-intercepts? Well, if I set each factor equal to 0, including this factor, I'd find out that we have 3x intercepts. Negative 2, 0, 2. Now, because this is a fourth degree polynomial with a positive leading coefficient, I know that both ends go up. So, what? That's not right. What if I do this? What? No, it's supposed to be up there. What's happening here? Why is my graph broken? Well, and the answer to that lies in the fact that this says x squared. Remember, when we have an even multiplicity on a factor, that means a bounce. So I am going to pass through at negative 2. I am going to pass through at positive 2. But at 0, I have to bounce. So I pass through, I bounce, and I pass through. Please don't make this look pointy. This should be concave down like a down-pointing parabola. Okay. What if instead I had y equals x minus 2, x plus 2 squared, and x to the third? I still have those same x-intercepts at negative 2, 0, and 2, but what do we know about the behavior? First, the degree. X to the third times x to the second is x to the fifth times x to the first is x to the sixth. So I know both ends go up. I'm going to pass through at x equals 2. I'm going to do what at x equals 3? Ooh, I know when I see an even multiplicity, I bounce. What was it that I do when I see an odd? Well, I'm not quite sure, so I'm going to deal with this middle point. For negative 2, I see that even, so I know at negative 2, I bounce. Now somehow I have to connect this to this. Do I do just that, straight through? No, silly. X to the third, we know x to the third. It's one of our reference graphs, or its friend, negative x to the third. Through this point, it has to look like this, or it has to look like this. And I need to connect this point with this point, so I'm going to go up and down. So I have to wiggle through that point. Now, in this situation, we wiggled through and it looked like a negative x to the third. But if I flip these powers and say, oops, did I graph that one wrong? I think I might have graphed that one wrong. If this was a 1, and this was a 2, and this was a 3, we pass through, we wiggle through, no, I graphed it properly, and no, might bounce at negative 2. There we go. Bounce at negative 2. Negative 2, 0, and 2. Bounce, wiggle, pass through. Yeah, so what I was saying is, what if we change these so that it's back to x squared, but this is negative 3? Okay, I still get a 6th degree polynomial if I were to FOIL this all out, but I now, at negative 2, am going to wiggle. At 0, I'm going to bounce. And at 2, I'm going to pass through. Okay? And finally, what if I had y equals x minus 2 squared, x plus 2 squared, x to the third? Okay, we've got negative 2, we've got 0, we've got 2. What degree is this polynomial? X squared times x squared is x to the fourth, times x to the third is x to the seventh. I don't see a negative out in front, so this odd degree polynomial, not odd function. We'll come back to that in a second. I know I'm supposed to bounce at negative 2. I know I'm supposed to bounce at positive 2. And I have to wiggle through at 0. So in order to connect this point with this point, will I be using a negative x to the third? No, that's not going to connect that with that. Instead, I want to use a positive x to the third. Okay? So we should be able to graph polynomials from their factored form, and we should be pretty comfortable factoring polynomials to get them into their factored form. We remember that multiplicity, when multiplicity of the factor is 1, then we're looking at just passing through the graph at that x-intercept. If we have an even multiplicity, we know we're going to bounce. I don't know if I'm going to bounce up or bounce down. I just know there's a bounce there. I won't know until I'm actually drawing the graph and get to that point whether my bounce goes up or my bounce goes down, right? I'll have to figure it out in context. Okay, one last thing about odd degree versus odd function. And this holds true for even degree and even function. Some people conflate these two things. So an odd degree function, y equals x to the third. That's an odd degree function, and it's an odd function. Why? Because if I plug in a negative x and a negative y, and then divide both sides by negative 1, I get back to the original function. So this odd degree function is an odd function. But if I take this and move it over 1, and move it over 1, this is not odd, nor is it even. Think about the graph. This shifts our graph right 1. Is this reflecting through the origin? If it did, this point 1, 0 would be matched over here by a point negative 1, 0. And if it did, this point 0, negative 1 would be matched by another point. I change the sign, 0, 1. But that's not happening here, right? These points aren't on this graph, so this is not an odd function. Even though it's an odd degree polynomial, it's not an odd function. So pay attention to the words. One little word, degree versus function, gives us two completely possible different meanings. An odd degree versus an odd function. Okay? Pay attention to those details. They'll be important. All right, what about this one from the last video? Can you graph that for me, please? Take a second to graph that. Come back when you're done. Pause the video. Okay, so, we can do this two different ways. We can think about it as our y squared relation shifted down 4. We could also understand this as a difference of squares. Y minus 2, y plus 2. And so we have y equals, so if I set x equal to 0, that's finding a y-intercept, I get y equals 2 and y equals negative 2. And because I have a positive leading coefficient, I know my parabola opens up that way. If I had a negative in front, my parabola would open up this way. Okay? In fact, let's do that in a different color because that's probably noteworthy. Yeah, remember, I'm expecting that you're taking notes on this stuff. So that's negative y squared minus 4. Is that negative y squared minus 4 or negative y squared plus 4? That's negative y squared plus 4. Negative y squared minus 4 negative y squared minus 4 is this graph. Now, how do I know that? Well, I know that for two reasons. One, I have to flip and then move it down. So I flipped this curve upside down and moved it down to make the black curve. But I can also think about this. What if I added 4 to both sides and then divided by negative 1 everywhere, and then took the square root? So if I plug positive, like I had originally thought it was this red graph with 0, 4, or 0, 4, yes. So if I plug in a 4 for y and a 0 for x, look what happens when you plug in a 0 for x. I have to plug in a 0 for x. 0 minus 4 is negative 4. Square root of negative 4, not a real number. That's plus or minus 2y. So this point isn't on this curve or these curves. So this point isn't on this. That's how I knew I had a mistake. Okay? All right, so we've gotten some more practice in graphing things, in particular by hand. I kind of want to come back and revisit piecewise briefly. So, but because we've gone through this in the last video, maybe you can do this for me. Let's say that g of x equals x squared minus 1 for x values less than or equal to 1, and 3x minus 2 for x values bigger than 1. Will you pause the video and graph this and come back when you're done just to check? Okay, welcome back. So we said two pieces. We would use two t-charts, one for each piece. Okay. This piece says use x's that are less than or equal to 1. And because it could be equal to 1, I put that closed circle there. This piece, 3x minus 2, is only for x values bigger than 1. But wait a minute, I have to put that breakpoint on both t-charts not equal to 1, so I use a little open circle for a reminder. Okay, so if I plug a 1 in here, 1 minus 1 is 0. If I plug a 0 in here, I get a negative 1. If I plug a negative 1 in, negative 1 times negative 1 is 1, and 1 minus 1 is 0. It doesn't surprise me, these points, because it's my regular parabola simply shifted down 1. So I've got 0, negative 1. I've got 1, 0 with an open circle, and negative 1, 0. And parabola. But my parabola stops here at 1. For x values bigger than 1, I'm using 3x minus 2. I do plug a 1 in there. 3 times 1 is 3 minus 2 is 1. So I know there's a point almost approaching 1, 1. If I plug in a 2, I get 4, and if I plug in a 3, I get 7. I know it's linear with a positive slope, and I find that easier than trying to make a bunch of hash marks and have it line up and still be a straight line. I can just label here 2, 4, and 3, 7. Okay, so there's our piecewise function. And, of course, I should be able to evaluate this. So g of 2, is g of 2 going to be 3 and 4? No, it's not both of those. Some students still give me 2 solutions for g of 2. G of 2 means I'm replacing x's with 2's. Well, this only works for x values less than or equal to 1. This is the one that works for x values greater than 1. So I'm going to plug my 2 into this x and get 4. As opposed to g of 0, 0 is less than or equal to 1, so I'm plugging my 0 in there to get a negative 1. And finally, g of 1, do I plug it into this one? No, because it doesn't have the could be equal to. I'm only plugging it into the top piece. And I end up with 0. And you see that on the graph right here. G of 1, when x is 1, the y value is 0. Okay? All right, so can you... I want to do 2 more things before we get to composition. All right, let's try... Why did that move over? It's so weird. All right, so here we go. Right, let's just... oh, you know what we need to do? We need to be able to graph this stuff on our calculator. All right, you do this one by hand. 2 square root 2 minus x for x less than or equal to 2, and x minus 2 squared for x greater than 2. You do this by hand, and then I'll show you how to do it on the calculator, okay? Welcome back. Did you have your 2t charts? X minus 2 squared and square root of 2 minus x. For x values less than or equal to 2. Closed circle, that's an open circle though. 1 and 0. 0? I like 0. I like negative 2. And the reason I like negative 2 is because minus a negative 2 is plus 2, 2 plus 2 is 4, square root of 4 is 2. If I plug in a 1, I get 1. If I plug in a 2, I get 0. So I know my graph goes through 2, 0, 1, 1, and negative 2, 2. Don't forget to label the points on the graph. What about this other piece of the function? If I plug in a 2, I get 0. Oops, that's a closed circle. If I plug in a 2, I get 0. If I plug in a 3, I get 1. And if I plug in a 4, 4 minus 2 is 2. 2 squared is 4. So I got 3, 1, and 4, 2. No, 4, 4. 3, 1. Hey, look at this. This open circle at 2, 0 gets filled in by this closed circle at 2, 0. So please, I said it before, I'm going to say it again, don't do that. If you draw an open circle and a closed circle at that point, I don't think you know what's going on here. What's going on here is there is an open circle at 2, 0, but it gets filled in by this closed circle. Okay, so graph that. I mean, that's what it should look like as a graph. It looks like a parabola over here, and it looks like a reflected square root over here. Okay, now I promised to show you how to do this on your graphing calculator. So I go to y equals, I guess I turn on my calculator, I go to y equals, and I'm going to type this first piece in, square root of 2 minus x. Now, this works only for x less than or equal to 2. And yet if I do a zoom standard, that is in fact all I see, right? Because it's a square root. The square root stops at its 0 point, which happens to have x equals 2. But if I now try and graph this in y2, x minus 2 quantity squared, I get this. And it doesn't stop, right? And this isn't a function. It fails the vertical line test over here. So I need to find some way to get my calculator to notice this restriction, okay? And so this is how we do that. All right, so we go back to y equals, and we type in divided by x. And what was the restriction? X is less than or equal to 2. So where do we find that? Well, we find that here under test. See where it says test here? Second math. Oops, I just did math. Second math. There we go. So I want x is less than or equal to 2. And so my less than or equal symbol is here, and 2. Okay? And I need to do the same sort of thing over here with the parabola divided by x, and now I want greater than, so second test, greater than, number 3, 2. Okay. Hello, I don't see parabola. I must have typed in something wrong. Let's go back and take a look. Square root of 2 minus x. X minus 2 squared. And graph. Okay, there's our square root. And there's our parabola. Sorry, forgot to tell you that you need to put this stuff in parentheses. So what is it that I typed? Just in case you couldn't see, y1 was square root 2 minus x, and then I said divided by, parentheses, x less than or equal to 2. And in y2, I typed in x minus 2 squared divided by x is greater than 2. Okie doke. So now you can graph piecewise on your calculator. Yay! Okay. The last thing, oh no. Yeah, we just did piecewise, and you know what happens when we do piecewise? I feel like you should go backwards. Open, closed. And I've got a third piece over here. Okay, and I want both of these open. I want this one open and this one closed. So you should be comfortable at this point writing the equation for this. So why don't you give it a try and then come back and we'll take a look at it together. Okay? All right. So here I have a linear function with a positive slope. I'm going up 1, but over 2, up 1, over 2, and the y-intercept would be 1. And this is going to be good for x values from -2 to 0. not equal to 0, just goes up to 0 and doesn't include it. Now here, the y value is 1/2. So I have 1/2, and that works for the x values between 0 and 3. At 0, however, I have a closed circle, so I need that. I have an open circle at 3, so I want that. And then finally, I have here, we're going from 1 to 0, so -1 is the change in y's. And what about the x increment here? The x increment, or the change in x, is going from 3 to 5, is 2. So I have -1/2. Well, I don't know what the y-intercept is. I know it's bigger than 1, but I can find out. So y minus 0 equals -1/2 x minus 5, or y equals -1/2 x plus 5/2. So we have -1/2 x plus 5/2, and that works for x values, that's an open circle, between 5 and 3. Okie doke. All right. The last thing I want to talk about today is composition. Composition of functions. Remember, f of g of x, g of f of x. This is that type of function reproduction where two functions make a new baby function where one function eats the other function. So maybe it's f that eats g to make little baby h of x, or maybe it's g that eats f to make little baby k of x. Okay? You know, we could also see this. F of x eats itself. Composition is where we shove one function into all the x's of another function. So let's start off with an easy composition. Oh, remember also the modern notation. This is a synonym for this. I like this one because it's easier for me to see I'm supposed to put g of x inside of f of x. I find it very hard to see that with this notation, okay? Just like this one could be written g of f of x, but I would prefer this. This to me says I'm supposed to jam f of x into all the x's of g of x. Okay, I want to actually start off with a gentle composition. So let's say that f of x equals x squared and g of x equals square root of x. Will you please tell me about h of x, which is f of g of x? Will you do that composition and tell me what you get? Did you get x? I didn't get x. So, yeah, let's do this. Let's ask our calculator to do the composition. Okay, so I'm going to take these out. Clear, clear. F of x is x squared, and g of x is square root of x, and I want to compose them. And the way we do composition is like this. We type in y1, y2. Okay? This has to be in parentheses. If we do this, that's multiplication. If we do this, our calculator says, oh, composition. Okay. So here, I'm going to do y1, parentheses, y2, close parentheses. Okay, so I'm doing the composition of x squared and square root of x. I'm actually going to turn off these graphs for a minute. I just want to see the composition. We think when we plug in square root of x into x squared, so I'm taking this and I'm plugging it in there and then squaring. We think we get that because square root and squaring undo each other, yeah? But I say no. So take a look at the graph, zoom, standard. So if this were the line y equals x, like we said it would be, where's the other half of the graph? It doesn't exist. So yeah, I agree squaring and square root they undo each other, but think about the domain, right? Little baby h of x has a restricted domain because dad has a restricted domain. Oh, remember what the restriction is on this? X is greater than or equal to 0. So, sure, our composition is x, comma, but only for x is greater than or equal to 0. Okay, this becomes important because without it, this graph should continue over here, and it doesn't. This only works, it's only x for x values greater than 0, and that's because of this restriction, or the restriction on the domain of that. What about this one? F of x equals x squared, and g of x equals square root of x, but this time, let's say k of x is equal to g of f of x, okay? Will you do that composition? Will you shove this in there and tell me what you get? Welcome back. So if I do that, I've got square root of x squared. And still many of you say this. All right, composition time. We want to compose y2, and now y1 is on the inside. And graph. Now, that's the line y equals x. That's not the line y equals x. That's absolute value of x. Even power. Absolute value. Think about plugging stuff in here. Think about your analysis skills. If I plug in a -4, -4 squared, -4 times -4 is 16, square root of 16 is 4. So if I plug in a -4, I get 4. If I plug in a +4, I also get 4. So it's not y equals x, because if I plugged in a -4, I should have gotten out a -4. But I plugged in a -4 and got out a +4. In fact, any value I plug in here will generate a positive output, except for 0. So absolute value of x. Yeah, we have to be a little more on our game. We have to be thinking more here. Okay, so when we did f of g of x in this situation, we got x, but only for x is greater than or equal to 0. And when we did g of f of x, that gave us absolute value of x. Okay? So be careful with composition. Don't be casual about it. Don't be afraid to check on your graphing calculator. All right, let's look at some other composition problems. Here's f of x equals x squared minus 2x, and g of x equals 4 minus 3x. And I want to figure out what f of g of x is. Not a graph, just what is this composition. And so I know I'm supposed to take g of x and plug it into all the x's of f of x. F of x has 2 x's. So I have to take all of g of x and plug it in here and plug it in here. So we're going to have 4 minus 3x squared minus 2 times 4 minus 3x. I do need you to FOIL this and distribute and combine like terms. Please do that. And then don't forget the combining like terms part. Minus 24 plus 6 is minus 18, x, and plus 8. So that's f of g of x. Now, could you please find f of g of 2? And there's 2 ways we can find f of g of 2. One is find f of g of x first, and then plug a 2 in. 9, 2 squared minus 18 times 2 plus 8. 4 times 9 is 36. 2 times 18 is 36. 36 minus 36 is 0, plus 8 is 8. But I could also evaluate this composition by finding g of 2. So I go up here and I find g of 2. That's 4 minus 3 times 2, or 4 minus 6 is negative 2. So g of 2 is negative 2. And then find f of negative 2. So now I'm going to plug the negative 2 in over here. And I have negative 2 squared minus 2 times negative 2. 4 plus 4, 8. So there's two ways I can evaluate the composition. First, actually compute the composition and plug the number in. Second, chase that through. Find g of 2 by plugging a 2 into g of x, then taking that result and plugging that in to f of x. Both should always work. I actually think that this method of finding g of x is a little more time-consuming just to plug the 2 in. I do think it's a little faster, maybe a little more efficient to plug the 2 into g, take that output, and plug that output into f. Okay? So, will u, with the same f of x equals x squared minus 2x, and g of x equals 4 minus 3x, will you find g of f of x? And then when you're done with that, I'm going to ask for g of f of negative 1. Okay, so why don't you take a minute to try that and come back, and then we'll be done with this lesson. So, welcome back. I know here that I'm supposed to take f of x and plug it into all the x's of g of x. So this goes in there. 4 minus 3 times x squared minus 2x. Please don't forget to distribute the negative to both of these. So 4 minus 3x squared plus 6x. Or negative 3x squared plus 6x plus 4 if we want to put it in descending order. Okay? Now to find g of f of negative 1, I can plug a negative 1 in here. And so we get negative 3 minus 6 is negative 9 plus 4 is 5. But we could also find f of 1, or f of negative 1. Negative 1 squared minus 2 times negative 1. And I get 3. And then take that 3 and plug it into g. G of 3 is going to be 4 minus 3 times 3, which is 4 minus 9, which is negative 5, and oops, I had negative 9 plus 4, and I wrote positive 5 when I was supposed to write negative 5. All right, so let's review. We talked about symmetry tests, x-axis, y-axis, and origin. We talked about even functions have y-axis symmetry, and odd functions have x-axis have origin symmetry. We talked about making sure we paid attention to graphs like this one, where it doesn't look like on our calculator it touches, but oh yes, it really does. We're not going to be surprised when we have to graph these x equals y squared things. And we talked a bunch about factoring polynomials and looking at multiplicity to determine any bounces, wiggles, or passes through. We reviewed graphing piecewise functions and evaluating piecewise functions. We talked about graphing piecewise functions on the calculator, and then we moved on to composition. And we pointed out the mind-blowing fact that the square root of x squared is not x, but is x for x values greater than 0. And we pointed out that the square root of x squared is not x, but in fact absolute value of x. Thank you, composition. We learned to practice composition, evaluating compositions. So I could do g of f of negative 1, because I know that's the same as that, where I evaluate f at negative 1 and then plug that y value into g of x. Or we could actually do the composition and then plug the negative 1 in. So we covered a lot of ground today. I hope you took notes on the stuff that you have never seen or didn't really remember when I was talking about it. Our homework tonight is, I believe it's bookwork? No, it's a worksheet. There's a worksheet in Office 365. Ooh, transformations quiz. Let's have one of those. Okay. I'll see you in the next video, everybody. Don't forget to reach out and group me to ask questions or during our live Zoom, our synchronous Zoom sessions to ask them. Okie doke? Take care.